Hello there again. I'm going to try to finish chapter 3 in this video. I hope you're doing well, but I think I'm going to have to do another video on chapter 3. But let's see. Okay, so let's get started again. Here is the section on inverse. And what we want to do is we want to find out a relationship between a function, the derivative of a function, and derivative of its inverse. So let's look at, first of all, something you know from algebra and pre-cal, that two inverses, the graphs of two inverses, are symmetric with respect to y equals to x, right? So these are two inverses. And also know, you should remember that finding an inverse is like switching x and y, right? So the y becomes the input, the x becomes the output. So if we have a point over here, and at this point the slope of the tangent line is q over p. Notice here q is the y value and p is the x value. Not x values, is a change in x and change in y. So if this point, the reflection of this point with respect to what? With respect to y equals to x, which is basically right here is in the middle, right? That's y equals to x. So the reflection of this point would be, of course, this point. And the slope of the tangent line at this point on this function, which is the inverse of that function. These functions are what? Inverses of each other. So notice that here the change of y over change of x is the slope. When we switch x and y, it would be the change of y becomes the change of x, and the change of x becomes the change in y, right? So if the slope here is q over p, right? Over here would be p over q, right? So it would be reciprocal of that. Now we have to kind of talk about this and see how we can actually find the relationship between an inverse of a function and the derivative of the inverse of the function, right? So let's see. And we talked about that already. So let me erase everything here. So the inverse function theorem looks like this. We're going to prove this. So it says that the inverse, the derivative of the inverse of a function equals to 1 divided by derivative of the function itself evaluated at the inverse, right? So basically, if this is the x value, right, then this is not x value. This is going to be the output of that x, right, which is the f inverse of x, right? All right, so let's look at where this formula comes from. We can easily prove it this way. You know, we know from algebra that if two functions are inverses, then f of f inverse equals to x, and f inverse of f of x equals to x. That's a simple idea. For example, let's say we have x to the third and cube root of x. These are inverses, right? So if you have a function here, let's say I put 2 in here, and then x to the third, of course, it takes it to 8, right? This is to the third power. So if I input 2 into this function, I get 8. If I take that output 8 and put it in this function, which is the inverse of that, right? So this is x. If I put it in there, what I get the 2 back, right? And if you do it the other way around, it's the same thing. If you start with 8, let's say I start with some number 8, and I let it go through cube root of x, this is 8. what comes out is 2. And if I let 2 go through x to the third, I get the 8 back, right? So whatever you start with, you get it back because these two operations cancel each other, right? So that's what this means. If you input the output of an inverse into function, you get x, and the other way around. All right, so we know that. So we're going to use this idea here. We say, okay, let f inverse of x be x, right? Now we know chain rule. We're going to take the derivative of both sides. What's derivative of a composite function? We just talked about it in the previous video, right? So the derivative of f of something is going to be f prime of something times the prime of something, right? That's the inside function. So the prime of f of something is f prime of something times the prime of that something, right? What's the prime of x with respect to x is 1, right? So we are going to isolate f inverse prime. We divide both sides by f prime of f inverse, and that's the inverse function theorem. So we proved that, right? So let's look at some examples. This is how it is given in textbooks, right? So basically it says that derivative of the inverse of a function is 1 over derivative of the function evaluated at the inverse, right? So if you think of, let's say, x to the third and think of cube root of x, right? So if I want to find, let's say, the inverse of this, which is the prime of this, derivative of this would be 1 divided by, right? So if I want to find derivative of cube root of x, I can do this. I say the answer is 1 over derivative of f, which is what? What's the derivative of f? So think of this as f, and think of this as its inverse, right? So derivative of f is 3x squared. I have 3x squared. I put this for x squared. But this x has to be the inverse. So I have to put what? Cube root of x here. So the derivative of cube root of x is 1 over 3 times cube root to the second power. That's the idea we're talking about here, and you can simplify this. So let's apply it and do a few examples. So here you go. Use the inverse function theorem to find the derivative of cube root of x. Well, we just talked about it. So we're going to consider this to be either this is the inverse and x to the third is the function, or we can think of this, right? So this is the function, this is the inverse, right? So this is f, this is the inverse of f, right? So g of x is the inverse of this. So now, again, as I said, the derivative, according to the inverse function theorem, is 1 over the derivative of x to the third is 3x squared, and instead of x I'm going to put what? Cube root, right there. And this would be 1 over 3x to what power? Well, cube root is actually x to 1/3, and x to 1/3 to the second, 2 times 1/3 is 2/3. Right, that's it. That's the answer. All right. Now, if we were to not use this and do it directly, what would we get? Do we get the same answer? Let's see. So we're going to do it directly without using this theorem. So this is nothing but x to 1/3, right? So what's the derivative of x to 1/3? Well, that would be 1/3 x to 1/3 minus 1, right? Which is 1/3 x to negative 2/3. And obviously negative 2/3 goes there, you get the same thing, right? Now, of course, you might say, why do we want to use this theorem if we can do it this easily, right? But the answer is that in many, many, many functions, well, finding the inverse is really hard. But instead of finding the inverse and finding the derivative of it, we can find the derivative of the inverse without actually knowing the inverse. Okay, so that's the idea. All right, so let's look at an example here. Extending the power rule to rational exponents. Now, with this idea, we can actually prove, remember this rule so far, we know is n x to n minus 1. We prove that if n is an integer, that actually works. But what about if n is a fraction? Well, now we're going to prove that that works too. How? Well, first we're going to look at an example, right? So find the equation of the line tangent to this graph. So we're going to do that. So to find that, g prime is going to be, we're going to use what? Use the power function using fractions. So g prime is 2/3 x to 2/3 minus 1, which is 2/3 x to 2/3 minus 1 is negative 1/3, and it goes in the denominator, becomes cube root of 8, right? So g prime is basically this right here. So let me write it in terms of x first. So it would be 2/3, right? And then x will be x to 1/3 here, which is 2/3 cube root of x, right? So that's g prime. Now what's g prime at 8? So we're going to substitute 8 in here. Well, we get 2. 2 times 3 is 6. 2/6 is 1/3. So the slope of the equation of the tangent line, the slope of the tangent line is going to be 1/3, right? So here you go. This is the y minus g of 8 equals to g prime of 8 times x minus 8, right? So g prime of 8 is 1/3. And g of 8, if you substitute 8 in here, g of 8 is, let me do that here. So g of 8 is just what? 8 to 2/3 power. Now you know from algebra that a to m over n is just nth root of what? A to m, or is nth root of a and then the quantity here to the mth power. That's the same thing. So that would be third root of 8. So that would be third root of 8 and then quantity to the second power, which is 4, right? So g of 8 is 4. G prime of 8 is 1/3. And so that's the equation of the tangent line. All right, now proof of the power rule for rational exponents. So what we want to do first, we're going to look at x to 1n, right? X to the power of 1n. Can we use power rule? The answer is yes. How do we prove it? Well, here's what we do. We're going to think of x to 1n as the inverse of x to n, right? Like, for example, x to 3rd, the inverse of it is x to 1/3, right? X to, second, the inverse of it is x to 1/2, right? So if you think of x to 1n as the inverse of x to n, we can use the inverse function theorem here, right? So derivative of this inverse would be 1 over derivative of that evaluated at that. So we're going to do g prime is going to be 1 over derivative of its inverse of the function that this is the inverse of, right? Of course, both of them are inverse of each other, right? But we're going to assume this is the function, this is the inverse. So derivative of this inverse would be 1 divided this derivative, which is n x to n minus 1, but instead of x, we're going to put the inverse, which is x to 1 over n, right? So that's what you get. So derivative of, let me write it here one more time to make sure. So x to 1n, derivative of this would be 1 divided by derivative of this, which is n x to n minus 1. But instead of x, we're going to put what? Instead of x, we're going to put this function, which is x to 1 over n, right? Now we simplify that. You have to multiply the powers, right? So n minus 1 times 1 over n was n minus 1 times 1 over n. Well, 1 over n times n is just 1 minus 1 over n, right? And if you give this a denominator of 1 and have the same denominator, then this would be n over n minus 1 over n, which is n minus 1 over n. So that's the power, right? So we're going to have n x to n minus 1 over n, right? And now we can simplify that. So what we're going to do is we're going to, so this is n minus 1. Remember in algebra that a minus b is the same as what? Is the same as negative b minus a. So instead of 1 over 1 minus n, I can write negative n minus 1, right? So over here, instead of 1 minus n here, instead of n minus 1, right, I could put 1 the other way around. Instead of n minus 1, we put negative 1 minus n, right? That's the same thing. So we can write n minus 1 here. Instead, we write negative 1 minus n, right, for that. And now, we've got, since this is a negative power now, we can bring it to the numerator. So n stays here, x comes in the numerator, becomes x to 1 minus n over n. And 1 minus n over n is 1 over n minus n over n, right? And that would be what? 1 over n minus 1 over n, and 1 over n minus 1 over n. So you can put a 1 here and think of it as 1 over n here. So that's 1 over n times x to 1 over n minus 1. So it looks like we just proved that x to 1 over n prime, you bring 1 over n downstairs, and then x to the power of what? 1 over n minus 1. That's exactly what the power rule is, right? So we just proved that even if it's a fraction, the answer here would be the same as the power rule, right? So apply power rule even if you have fractions, right? All right, now this is 1 over n. What about m over n? So we can extend this to m over n here, you see, because x to m over n, actually, we can write it as x to 1 over n to the power of m, right? And then the prime of this, we can bring this m downstairs, right? Because this is to a power, right? So by chain rule, this is a function and this is a power. So by chain rule, derivative of this would be derivative of something to the mth power, which is m something to m minus 1, times the derivative of inside. What's the derivative of that? We just proved the derivative of that is here. So we're going to put that there. And if you simplify this, right, if you simplify, you see that you get the same idea. That if you have x to m over n prime, you bring m over n here, and then x to the power of m over n minus 1. So that means the power rule can be extended now to a power of a fractional power, m over n, right? So we proved it. Of course, you don't have to prove it to use it, but that's what it is. All right, now one of the reasons we like this idea of inverse is that we can find the derivative of inverse trigonometric functions. Remember that trig functions have inverses: sine, cosine, tangent, secant, cosecant, cotangent, they all have inverses. So what we do is this. Suppose we want to find the derivative of the inverse of sine, right? What is that? Well, we're going to think of this as the inverse of f of x equals to sine x, right? So that's the inverse of this. So what's the derivative of inverse? Again, by our theorem, derivative of inverse is 1 over derivative of the function evaluated at the inverse. So what's the derivative of sine inverse? Is 1 over derivative of function, which is derivative of this. What's the derivative of sine? Cosine, right? So derivative of sine inverse is 1 over derivative of sine evaluated at the inverse. So instead of x, we put the inverse there. All right, so that's what we get. But the problem with this is that we got sine inverse inside cosine. But you understand that sine inverse actually, when we write sine inverse of, let's say, 1, what does that mean? It means that I'm looking for an angle whose sine is 1. And that angle, of course, is 90 degrees, right? So, so here, when we write sine inverse of x, for that, we're looking for an angle whose sine is x, right? So what we can do is this: we can draw a triangle and have this to be the angle we're looking for. We put it right here. This is theta we're looking for. And so the sine of this theta has to be x. Remember, sine is opposite over hypotenuse, right? So opposite of this has to be x, and the hypotenuse should be 1. This way we can get sine to be x, right? So what's the sine of that? X over 1, which is x, right? So that is the angle we're looking for. So instead of sine inverse of x, we're going to put cosine theta here. And now from this triangle, we're going to find what cosine of this angle is. We know the sine is x. And if you think about it, in this triangle is a right triangle. So if this is x, this is 1, this would be square root of 1 minus x squared, right? Because c squared equals to a squared plus b squared. And from there, we can find that this side is a hypotenuse squared minus this side is squared, and take square root. So the cosine of this angle is going to be adjacent over hypotenuse, and that would be square root of 1 minus x squared. Now, since here is sine inverse, remember sine inverse, the restriction for sine inverse is that we are between negative pi over 2 and pi over 2. That's the restriction for sine inverse. So here, in this region, cosine is always positive. So that means we don't have to consider another triangle over here and figure out what happens if cosine is negative. Cosine is not negative here, right? Anywhere else, yes, cosine could be negative here and here, but for sine inverse, the domain is restricted to get the sine inverse, and the restriction is from negative pi over 2 to pi over 2. So in this restriction, right, the cosine is positive, so we just substitute for cosine theta is square root of 1 minus x squared. And obviously the domain here has to be what? X is between -1 and 1, and x cannot be -1 and 1. Why? Because the denominator becomes 0. So that's why we didn't put equality here. So theta is between -pi/2 and pi/2. All right, so now we have an expression for what? For the inverse of trigonometric function, sine. And notice that this is an algebraic function, but this one is transcendental function, right? So algebraic function is a function you can actually write a formula with operations, you know, in algebra: addition, subtraction, raising to power, taking root, right? If you can do that and get an expression, then we call that an algebraic function. And notice for the trig function, we don't have that, right? So the answer to the derivative of sine inverse is this right here. So you can remember this as a formula. So derivative of sine inverse of something is going to be 1 over square root of 1 minus something squared. Now that's something instead of x, we put u there, because the argument of sine inverse could be another function, right? So it doesn't have to be x, it could be anything else. But we know chain rule. Since we know this formula, then we say the derivative of sine inverse of something is 1 over square root of 1 minus u squared, something squared, times the prime of whatever that is, right? So for example here, what's the derivative of this? Well, the derivative is going to be 1 over square root of 1 minus something squared. What is that something? That. 2x to the third. And then multiplied by derivative of that something, which is 6x squared, right? All right, so that's the idea. Let me give you the answer. It would be 6x squared over 1 minus square root of 1 minus 4x to the 6. 2 to the second is 4, and x to the third to the second is x to 6. You have to multiply the exponents, right? All right. Now, what about the next trig function, inverse trig function, cosine inverse? Well, we use the same trick. We consider cosine inverse to be the inverse of cosine, and then we say, okay, what's the derivative of cosine inverse? I would be 1 over derivative of this, which is negative sine of cosine inverse, right? And again, the same trouble we have, just like the previous one. Cosine inverse of x is actually an angle we're looking for. We're looking for an angle whose cosine is x. Again, we use the same trick. We draw a right triangle, and we put this angle over here, and we say, okay, how can the cosine of this be x? Well, the only way is if this is x, and this is 1, right? So x over 1 is x. So in this triangle, theta has cosine x. So we're going to put theta here, and we end up with sine theta. So we got to find sine theta now. Again, if this is x, this is 1, that side would be square root of 1 minus x squared. And remember from trigonometry that when we talk about cosine inverse, the restriction for cosine inverse is over here, right? From 0 to pi. And in this region, sine is always positive. So this sine is actually positive. And we don't have to worry about the plus and minus. We just consider that to be positive. Now, theta cannot be, again, 0 or pi. Why? Because the denominator becomes 0. So the domain would be that, right? So the inverse, the domain of the derivative is different from the domain of the inverse, right? Why? Because what derivative is its own function. Because functions can have derivative over their entire domain, or maybe part of the domain the derivative is not defined. That's okay. All right, so and notice that the derivative of cosine inverse is negative. And that's the same pattern that we had with trig functions too. All the cofunctions, the derivatives were negative. It is true for inverses too. So derivative of cosine inverse is negative 1 over square root of 1 minus x squared. Or in general, if you think of derivative of cosine inverse of something, would be negative 1 over square root of 1 minus something squared times that something prime, the derivative of whatever that is. So in this case, that is negative 3x to the fifth. So derivative of that would be negative 1 over square root of 1 minus this whole thing squared times derivative of this whole thing, which is negative 15x to the fourth. And the rest of this is just simplifying, right? So you can stop the video and make sure you get this. And I'm going to move on to the next function, inverse function. What about tangent inverse? Well, we use the same trick. We are going to think of tangent inverse as the inverse of tangent, right? And we know the derivative of tangent is secant squared. So we are going to think of derivative of tangent inverse as 1 over derivative of tangent, which is secant squared. So 1 over secant squared of tangent inverse. And the tangent inverse again is an angle whose tangent is x. Again, we use the same trick. We have a right triangle and we need an angle whose tangent is x. What's the definition of tangent? Opposite over adjacent, right? So if the angle here, theta, wants to have tangent that is equal to x, this x, if you make this x and make this 1, it works, right? So this angle now has a tangent of x. So now, so instead of tangent inverse, we put theta. We mean this theta, right? And now, what is secant squared of theta? Well, again, when we talk about tangent inverse in pre-calculus, we know that the restricted domain, again, would be between negative pi over 2 and pi over 2, right? And over here, cosine is positive, and we know secant is 1 over cosine, so secant also would be positive. So when we want to find secant, first we find cosine, which is adjacent over hypotenuse, and then we flip it. We flip this, we get secant. So that's the secant, and it has to be positive. So secant squared would be 1 minus x squared, right? So here we go. And here, there is no restriction for the domain, right? There is no restriction, so the domain of the derivative of tangent inverse is all real numbers. Okay, so we can say the derivative of tangent inverse is 1 over 1 plus x squared. Derivative of tangent inverse of something is going to be 1 over 1 plus something squared times the derivative of something, right? So in this example, this is the something, right? So what's the derivative of tangent inverse of negative 4x to the third? Well, 1 over 1 plus this thing squared times derivative of this. And the rest of it is algebra. Again, stop the video, maybe you can go through this, write these formulas down. They're in actually formula charts, but just practice with them. Here is the next one, cotangent inverse. Again, we use the same trick. Cotangent inverse is the inverse of cotangent. And we know the derivative of cotangent is negative cosecant squared. So what's the derivative of cotangent inverse? Is 1 over derivative of cotangent evaluated at the inverse. So the derivative of cotangent inverse is 1 over derivative of cotangent, which is negative cosecant squared, of cotangent inverse. Now again, cotangent inverse is an angle whose cotangent is what? Is x. Again, the same trick. Here, theta, and so cotangent is adjacent over opposite, so x over 1, right? So if we set it up this way, then cotangent of this angle will be x. So now, cotangent inverse is actually theta, so this is negative cosecant squared theta. So we're looking for cosecant squared theta here. Cosecant is 1 over sine, right? And so we find sine. What is sine is, now if this is x, this is 1, this side would be 1 squared plus x squared, because this is the hypotenuse, right? So it's the square root of x squared plus 1, or 1 plus x squared, the same thing. I'll put 1 plus x squared here, what doesn't really matter. So sine is 1 over the square root of x squared plus 1. So sine squared is going to be 1 over x squared plus 1. So cosecant squared is going to be, so you can put sine squared here, is 1 over x squared plus 1. And then cosecant squared is the reciprocal of this, so it's just x squared plus 1, right? We just need cosecant squared, we don't need cosecant. I just found it here, but cosecant squared is right. So we're going to take this and substitute it for cosecant squared, right? I'll put this negative in the numerator. Again, you see the pattern that derivative of cotangent inverse is negative, right? All right, so let's do an example, and we use same idea that derivative of cotangent inverse of something is going to be negative 1 over 1 plus something squared times something prime. In this case, this is the something, so the derivative would be so derivative would be negative 1. Looks like I'm missing something here. Did I miss a negative? Looks like I do, right? So let me put a negative here and fix it later. So it's going to be negative 1 over 1 plus this thing to the second power times derivative of this, which is negative 6x squared, right? So this is going to be, so this is going to be negative. This negative makes it a positive. There you go. Fixed it. All right, so that's derivative of cotangent inverse. Now, what about secant inverse? Well, again, we're going to think of secant inverse as inverse of secant. And we know derivative of secant is secant tangent, right? So what's the derivative of secant inverse of x? Is 1 over derivative of secant, which is secant tangent. But these inputs have to be what? Have to be the inverse secant. So it's 1 over derivative, which is secant tangent, and then instead of x, we put secant inverse, right? And the secant inverse is actually, again, is what? This actually is an angle whose secant is x, right? Now, secant is 1 over cosine, so that means if the secant is secant of theta is x, then cosine of it has to be what? 1 over x, right? So we're going to set up the triangle such that the cosine of this angle is 1 over x. So adjacent over hypotenuse has to be 1 over x. If this is 1, this is x, then this is the square root of x squared minus 1, right? And now we're going to, again, do the same thing. Oops. Let me go back. There you go. So I'm going to do the same thing here. So I'm going to think of secant inverse as theta. So we substitute theta. And now we're looking for secant theta, tangent theta. We know secant theta is x, and tangent theta is what? Opposite over adjacent. So tangent is the square root of x squared minus 1. Okay? Now, why is it here, why is it that we put absolute value? Because secant is x, right? Secant theta is x. So this is basically x times the square root of x squared minus 1. And why do we put absolute value? I'm going to try to explain that in the next slide. Okay? So that's the formula. Now, why do we put absolute value of x? Now, what we want really is that in the denominator, we're going to have plus and minus x times plus and minus the square root of x squared minus 1. Because in the restricted domain that we have for secant, when we find the inverse of secant, the restricted domain is going to be from 0 to pi, right? Except pi over 2 is not included, right? Because pi over 2 makes the cosine 0, and you can't have 1 over 0. So the domain is going to be basically 0 is going to be from 0 to pi over 2 and from pi over 2 to pi. Now, if we are from 0 to pi over 2 over here, then cosine, tangent, and sine, they're all positive, right? Over here, they're all positive. And if we are from pi over 2 to pi, then cosine is negative, sine is positive, and tangent is negative, right? Cosine and tangent are positive, negative, and sine is positive. So secant theta times tangent theta, which is the denominator of our expression, right? Secant times tangent, that is going to be positive in 0 to pi in both cases, even though the sign of these change. But when you multiply secant times tangent over here and over here in this domain, in this interval and this interval, in both cases, this has to be positive. Even though secant and tangent change sign, but they change sign in a way that when you multiply them, you still get positive. Over here, they're both positive, right? But over here, they're both negative. Because secant is 1 over cosine, which is negative. Tangent is here negative. Negative times negative is positive. So that's why we put the absolute value to make sure this product is actually positive. Of course, we put the square root. Square root is always positive. We don't put plus and minus. We just put square root, so that's positive. And then if we put x without the absolute value, then when x is negative, this is going to be negative, right? And that's not correct, because we know the product is always positive. So that's the idea, okay? That's why. So in this case, we have actually two triangles. We have to create two triangles. One, let me draw the coordinate plane. So one triangle would be over here, right? And the other triangle would be over here in the second quadrant, like that. So that's why we have two different regions we have to worry about. But since the product is always positive, we have to put absolute value. All right, now that we know, then we're going to use the formula for secant inverse. So what's the inverse? What's the derivative of inverse, secant inverse? Derivative of secant inverse is 1 over absolute value of something, whatever is in here, then a square root of something squared minus 1. That's the structure. And then you have to multiply by the prime of something. All right, so if you think of it that way, then it's really easy to take the derivative. What's the derivative of secant inverse of something is 1 over absolute value of something, square root of something to the second minus 1, times derivative of something. Now you're done. The calculus is done here. The rest of this is simplifying. You can simplify it, but that's what you get. All right. And the next one, cosecant inverse, we use the same trick. Again, cosecant inverse is the inverse of cosecant. And we know the derivative of cosecant is negative cosecant cotangent. And so the derivative of cosecant inverse is 1 over derivative of cosecant, which is negative cosecant cotangent. So 1 over negative cosecant cotangent, but the inputs have to be cosecant inverse. Here I directly just put theta there because that is theta, right? By now you know, I skip one step here. By now you know it. So the theta has to satisfy what? The fact that cosecant of it has to be what? X. Well, we know cosecant is what? Cosecant has to be x, but cosecant is 1 over what? 1 over sine. That means the sine of it has to be 1 over x, right? So we have to set this up so that opposite over hypotenuse is 1 over x. And this is square root of x squared minus 1. So now we have what? We have the triangle that we want. So now we need to substitute cosecant. Well, we know cosecant is x, of course. And cotangent is going to be square root of x squared minus 1. Right here. Cotangent is adjacent over opposite. Now, again, the reason we put absolute value is the same thing. In this case, the restricted domain is from negative pi over 2 to pi over 2. But 0 is not included because at 0, sine is 0, and 1 over sine is gonna cause trouble, right? So in this region and in this region, just like I explained before, right? The signs, there are some sign changes, but the product has to be positive, this product. Since we put square root, and a square root is always positive, if I just put x here, right, then when x is negative, this would be negative, and that's not correct. The numerator is negative, that's part of this formula. We put that negative in the numerator. Okay? So that's the formula, and the domain, we talked about the domain. Let's see, did I talk about the domain last time? No, but we're going to do it at the same time. So here, so the domain would be absolute value of x is greater than 1. Why? Because x squared minus 1 has to be positive. For that to be positive, the domain would be the whole here at 1, the whole here at negative 1. Everything here is good, and everything here is good. They make the under the radical positive, right? If you put anything between negative 1 and 1, under the radical would be negative, and that's not allowed. Okay, so the formula is, again, notice that there is a co, so the answer is negative. So the derivative of cosecant inverse is negative. So here's an example again. Now here's a little bit more involved. Since we got good at this, in this problem we do a chain rule as well. Get a chain rule involved, right? So what do we have here? We have a fifth root of something. Now fifth root means what? Means this whole thing to 1/5 power. So here we have 1/5. We have something to 1/5, right? What's the derivative of something to 1/5? Is 1/5 times whatever, I call them thing 1, thing 2. So we can think of it as two different things here. The first one applies to this outer function. So the outer function is the thing 1 here, right? Here's the thing 1. So what's the derivative of thing 1 to 1/5 power? Is 1/5 thing 1 to 1/5 minus 1, which is negative 4/5, times thing 1 prime, right? And now, when we talk about thing 1, that would be this whole thing, right? So now, what is the derivative of that? Well, the derivative of that is the derivative of cosecant inverse of thing 2. So that's the thing 2, negative x squared. So what's the derivative of that? Let's see. So we got derivative of cosecant inverse of something is going to be, again, negative 1 over absolute value of something, right, times the square root of something squared minus 1, times the derivative of something, right? All right, so that's the structure, so let's do it. So derivative of something to 1/5 power would be 1/5 something to negative 4/5 times the derivative of something. But derivative of this thing is what we just learned how to do. Derivative of cosecant inverse of something is negative 1 over something, right? That's the something right here. Absolute value of that. Square root of that, squared minus 1. And then times the derivative of that. Now we're done. This is the calculus part of it. The rest of this is simplifying. You just simplify this thing, you know. So we can put this in the denominator or put it back in a radical form, right? And so this would be x to the 4th power minus 1, right? And this right here goes in the denominator and would be the 5th root of this thing to the 4th power, right? So it would be the 5th root of this thing to the 4th power, right? That's that. And this part of it, this is x to the 4th. And now we could put them all together under one fraction. All right. So we got the inverses under control. These are the graphs of them. So derivative of sine inverse equals to that. And we got the derivative of sine inverse here. Right, this is sine inverse. Right? So derivative is positive always. Now think of the slope of the tangent line for this graph is always positive, and that's why derivative is always positive. Cosine inverse right here is negative, and notice that the tangent line is always what? Has a negative slope, and so forth. You can stop the video and try the rest of these and convince yourself that the sign of the derivative is actually correct. Okay? All right. So I'm going to make another short video on this chapter, and that would be on implicit differentiation. Okay? So I'm going to stop here. I did a few corrections here. So I'm going to come back here and say bye to you and see you in the next video. Take care of yourself and others.